In the depths of the cosmos, where silence reigns and light has no meaning, the life of a massive star is a story of balance. For millions of years, gravity pulls inward with relentless patience, while nuclear fire pushes outward with equal determination. Every heartbeat of that star is a negotiation between collapse and expansion, a cosmic standoff written in hydrogen and heat. Deep in its core, atomic nuclei fuse together, transforming light elements into heavier ones, releasing the energy that holds the star's weight against its own immense gravity. But no flame lasts forever. When the fuel runs dry, the balance falters. The final act begins quietly, as the core fills with iron, the element that gives nothing back. Unlike lighter elements, iron resists fusion. It cannot release energy. It only consumes it. The star's heart cools, and gravity, long restrained, begins to tighten its invisible hand. The pressure grows beyond measure. Then, in an instant, the core collapses. The outer layers, once tranquil seas of plasma, fall inward at a fraction of the speed of light. Within a heartbeat, the vast body of the star crushes down upon its center. Protons and electrons are forced together, merging into neutrons. In that single moment, densities climb to levels where a teaspoon of matter would outweigh mountains. Temperatures soar beyond billions of degrees, and then a rebound. The collapsing core stiffens, halts, and flings the outer layers back into space. The universe witnesses a supernova, a detonation so fierce it can outshine an entire galaxy for a brief and terrible moment. Shock waves ripple through the interstellar dark, scattering the atoms once locked inside the star's heart. Gold, oxygen, iron, carbon, every element that will one day build planets, oceans, and living minds now drifts through the void. The death of one star becomes the birthright of countless worlds. Yet not all that the star was is lost. The core that remains is change beyond imagination. If its mass lies below a certain threshold, about 1.5 times the mass of the Sun, it halts its own collapse. The pressure of neutrons, governed by quantum laws that defy common sense, pushes back against gravity's crush. This is no ordinary object. It is a neutron star, a sphere no larger than a city, yet heavier than the solar system's entire family of planets combined. Its surface is made of atomic iron fused into a solid crust. Beneath it lies a sea of degenerate matter, a strange ocean where atomic nuclei have melted into a continuous field of neutrons. The gravity here is beyond comprehension. To stand upon such a world, if standing were possible, would mean bearing a weight 200 billion times greater than on Earth. A single step would crush any known material. A grain of sand dropped from a meter above would strike the surface at nearly half the speed of light. But there are stars whose hearts grow heavier still. If the collapsing core surpasses that fragile boundary, even the quantum strength of neutrons cannot resist gravity's hunger. The collapse continues without end. Matter sinks inward, space folds upon itself, and time stretches toward infinity. No surface remains, no solid ground, no light. What is born in that silence is a black hole, an object without an edge, where the very geometry of space-time caves inward. A black hole does not possess a surface as a planet or a star does. Instead, it is defined by a boundary, the event horizon, beyond which all paths lead inward, even those of light. Once crossed, nothing returns. The star that once shone across galaxies becomes a shadow in space-time. Its mass still there, its presence still felt, but its light forever gone. Between the neutron star and the black hole lies the narrowest of frontiers. A difference of mere fractions of solar mass decides whether a dying star will stabilize or be consumed by its own gravity. It is the thinnest line in astrophysics, a boundary written by Einstein's equations and nature's indifference. One star halts at the brink, becoming a monument to matter's resistance. Another steps a little too far, and the universe folds it away from view. And yet both are children of the same death. Both are born from collapse and silence, from the final surrender of fusion's light to gravity's will. Their story is not only about destruction, but about the transformation of energy into geometry, of matter into curvature. Gravity, that most patient of forces, reshapes the universe, not through violence, but through inevitability. To understand what separates the neutron star from the black hole, we must go beyond mass and pressure, beyond fusion and collapse. We must understand gravity not as a pull, but as the very shape of the cosmos itself, a bending of space and time that determines the fate of everything that ever was and everything that will be. When we speak of gravity, we often imagine it as a force, a simple attraction that pulls one object toward another. Yet, this is only the surface of the truth. In the deepest sense, gravity is not a pull at all, but a curvature. It is the shape of reality itself. When Einstein reshaped our understanding of the cosmos, he taught that mass and energy do not merely sit in space. They tell space how to bend, and space tells matter how to move. A planet orbits a star not because it is tugged by an invisible rope, but because the space-time around the star is curved. Like a marble rolling across a stretched fabric, the planet follows the geometry carved by the star's mass. The heavier the star, the deeper the curve. And when that mass grows unimaginably dense, the fabric does not merely dip, it folds. Inside a neutron star, this curvature reaches extremes that defy all human scale. The gravitational field near its surface is hundreds of billions of times stronger than that of Earth. Even light, the fastest thing in the universe, must struggle to climb away. A photon emitted outward is drained of energy as it escapes, stretched to longer and longer wavelengths, until what once was brilliant becomes faint and red. The neutron star's light, when seen from afar, is not what it truly is. Its gravity changes even the color of its being. If we could somehow hover above such a surface, though no human vessel could withstand the pull, we would see strange distortions. The curvature is so severe that we could gaze forward and see part of the back of the star. Space folds the view upon itself. Up and down lose their meaning. The very notion of distance is twisted by geometry. Yet as powerful as this is, a neutron star is still a realm where physics retains form. There is still matter. There is still a surface. The laws that govern atoms, though strained to their limits, still hold. Quantum pressure resists collapse. The star exists in defiance of gravity, a frozen moment where the universe says, "Here is as far as matter can go, and still remain matter." But if the mass of the remnant crosses that invisible threshold roughly 3 times the mass of the sun, the story changes completely. Gravity does not stop at resistance. It deepens. The curvature becomes so steep that no known law can oppose it. In that instant, the star's own identity ends. Its radius shrinks to a point defined only by mass, charge, and spin. Around it forms the event horizon, a region from which light cannot return. To an outside observer, time itself appears to freeze at this boundary. The final fall never finishes. It only approaches completion forever. From afar, we cannot see what lies within. The black hole's heart is shielded not by material, but by the structure of space-time itself. Beyond the horizon, every direction points inward. Every possible path ends in the singularity, a region where the equations break, where density and curvature grow without bound. Whether the singularity is truly a point or something else entirely, perhaps hidden by quantum gravity, remains one of the deepest mysteries in physics. The difference between the neutron star and the black hole, then, is not a question of degree but of kind. A neutron star still belongs to the universe. Its surface radiates light. Its magnetic fields pulse across the cosmos. A black hole stands apart. It is not an object within space. It is a boundary of space itself. The event horizon is not a surface one can touch. It is the limit beyond which reality, as we know it, ceases to be accessible. And yet, the same law shapes them both. Gravity, described by Einstein's field equations, connects mass and curvature in perfect proportion. The greater the mass, the deeper the curve. Compress that mass enough, and curvature no longer forms a gentle well but a bottomless pit. The difference between the two remnants, the neutron star and the black hole, lies in how far the collapse proceeds before equilibrium or surrender. Even in that surrender, beauty remains. Around both kinds of objects, the universe glows. Space bends, light arcs, and time stretches. Each becomes a natural laboratory for the laws of physics pushed to their absolute limit. The neutron star is the last stand of matter, the black hole, the victory of gravity itself, and together they define the edges of possibility, the frontier where existence meets its own reflection. The next step in understanding them is not to look from afar, but to descend, to imagine what it means to stand, if one could, upon the surface of a neutron star, and to feel the unrelenting weight of space-time, pressing down from all directions. Only there can we begin to sense what gravity truly is when it has nearly won. To picture a neutron star is to imagine the impossible made real. It is no longer a sphere of flame or gas, but a solid monument of collapsed matter, smaller than a single city yet holding more mass than the Sunday Bay. Its crust, only a few centimeters thick in places, is composed of atomic nuclei packed so tightly that they resemble a crystalline lattice of pure nuclear iron. Beneath that, the atoms dissolve, their electrons merging into protons, creating a sea of neutrons so dense that a single teaspoon would weigh billions of tons. If a human could stand upon its surface, though no form of life could survive there, the experience would be beyond comprehension. Gravity would crush any structure instantly. Even the most advanced material conceived by imagination would collapse into vapor. The acceleration of free fall would reach hundreds of billions of times that of Earth. A body dropped from a meter above the surface would strike in less than a microsecond, moving at a significant fraction of the speed of light. The surface itself glows faintly, not from heat in the ordinary sense, but from the decay of subatomic reactions left over from its violent birth. The temperature can reach over 1,000,000 degrees Celsius, yet the light that escapes is filtered through gravity's redshift, emerging weaker and redder to any distant observer. If one could see the star from a safe distance, it would shimmer as a dim, ghostly sphere, surrounded by the curved halo of its own bent starlight. Yet the neutron star is not static, it spins. Conservation of angular momentum dictates that as the original star collapses, its rotation speeds up dramatically. What once took days can now take milliseconds. Some neutron stars rotate hundreds of times each second, their magnetic fields amplified to monstrous strength. The magnetic poles sweep through space like cosmic lighthouses, beaming radiation in narrow cones. When one of those beams crosses Earth's line of sight, we detect a pulse, a perfect clock, ticking across the galaxy. Thus was born the term pulsar, the heartbeat of a dead star. The magnetic field of a neutron star is trillions of times stronger than Earth's. Near the poles, particles are accelerated to near light speed, emitting bursts of radio and X-ray energy. These are not random signals but precision pulses, as steady as the rhythm of an atomic clock. Each pulse carries the fingerprint of extreme physics, the dance between gravity, magnetism, and quantum mechanics, at the edge of endurance. But even in its stillness, the neutron star is restless. Over millions of years, it will cool and fade, its radiation dimming as it slowly releases its stored heat into the cosmos. Yet before that, it can become part of something grander. If paired with another neutron star in a binary system, their mutual gravity draws them together. They spiral closer, radiating gravitational waves that ripple through the fabric of space-time itself. Eventually they merge, releasing more energy in a fraction of a second than the sun will emit in its entire lifetime. The collision produces a kilonova, forging heavy elements like gold and platinum, the treasure of the universe born from catastrophic unions. In contrast, when a black hole forms, the story takes a darker turn. There is no surface, no solid crust, no magnetic beacon. There is only the event horizon, the boundary where escape becomes impossible. Yet from outside, the black hole can mimic the gravitational pull of any other mass. If the Sun were replaced by a black hole of equal mass, Earth would continue its orbit unchanged, circling the same gravitational center, though the light of day would vanish. What makes a black hole terrifying is not its pull at a distance, but what happens near the horizon, where space curves so violently that time itself begins to slow. As we compare these two extremes, the neutron star and the black hole, we begin to see that gravity's nature is not about strength alone. It is about geometry. In one, space is stretched to the edge of breaking, yet matter still exists. In the other, geometry collapses into itself, leaving only the echo of mass. The neutron star is gravity restrained by quantum law. The black hole is gravity with no restraint at all. Both arise from the same stellar death, yet their destinies differ by the slightest measure. A fraction more mass, a little less resistance, and the balance tips. The neutron star becomes a black hole, the visible becomes invisible, and the universe loses another light to the darkness. Still, the two remain bound by the same cosmic thread. Each reveals a different face of gravity, and to understand their difference is to glimpse the structure of reality itself. The collapse of a star is not an ending, but a transformation from the language of matter to the language of space-time. In that transformation lies the foundation of every mystery to come. For the story of gravity does not end with collapse. It deepens. It draws us closer to understanding how space bends, how time slows, and how the universe itself is written in the geometry of the unseen. Gravity is often imagined as a simple attraction, a mysterious pull between objects. Yet in truth, it is far deeper than any tug or force. It is the shape of reality itself. Einstein's vision transformed this understanding forever. He showed that matter and energy bend the stage upon which the universe unfolds, that what we call gravity is not a hand pulling downward, but the curvature of space-time. A planet moves around a star not because it is drawn in, but because it follows the straightest possible path through a curved geometry. The greater the mass, the deeper the curve, and the more space itself bows around it. In everyday life, we live upon this curvature without ever feeling its depth. Earth's gravity bends space-time only slightly. Light passing by the planet is deflected by less than the width of a human hair over hundreds of kilometers. Yet the principle remains. Even the smallest mass changes the geometry of its surroundings. In the heart of a neutron star or near a black hole, this principle grows into something almost beyond conception. Einstein's equations, delicate and balanced, describe how space-time curves under mass and energy. The greater the density, the more the curvature tightens. If one could look at space around a massive object, it would appear as a vast invisible whirlpool, each line of geometry twisting inward. But unlike a real whirlpool, there is no water and no center that can be seen. The curve is the structure itself. When a massive star collapses, its core compresses until density becomes the defining feature. A neutron star packs the mass of 1.5 suns into a sphere only about 20 kilometers across. The curvature of space-time at its surface is so steep that even light, though fast enough to cross the universe, loses energy as it climbs away. Photons stretch into redder tones, and time slows for everything near that surface. The heartbeat of a clock there would appear slower to any distant observer. This effect, called gravitational time dilation, is one of the most astonishing results of general relativity. Time, which we often treat as absolute, is not the same everywhere. It flows differently depending on gravity's strength. Near a neutron star, a single second can pass more slowly than a second far away in the quiet void. In a black hole's gravity, this difference grows so extreme that at the event horizon, time appears to stop entirely. From a distance, no event inside can ever be seen to finish. The collapse of matter seems frozen forever on the edge of disappearance. To the matter itself, however, there is no pause. Space and time are so intertwined that as one slows, the other bends. Falling into a black hole is not like moving through space, but like sliding into the geometry of time itself. The event horizon marks the boundary where every possible path leads inward. No force can resist it, for it is not a pull. It is the shape of reality. Near the surface of a neutron star, the same geometry is present, though less absolute. Gravity is immense, but it can still be measured, still be countered by the neutron pressure within. Space-time bends, but does not close. The star's magnetic fields and radiation can still reach the universe. Its spin still sends pulses across the galaxy, keeping time with cosmic precision. In a black hole, no such exchange is possible. There is only the horizon, silent and one way. The difference between these two extremes is one of curvature and boundary. Imagine space-time as a stretched fabric. A neutron star presses deeply into it, forming a steep valley but leaving the fabric intact. A black hole tears through entirely, creating a hole so deep that nothing can climb out. The neutron star shows us gravity's power restrained. The black hole shows us gravity's final form, where the geometry itself folds inward and space becomes time. Every measurement we make, the bending of starlight, the timing of pulsars, the detection of gravitational waves, confirms this vision. Space and time are not passive. They are dynamic, flexible, alive. They ripple when disturbed, stretch under mass, and can even vibrate when the universe's heaviest objects collide. These ripples, traveling at the speed of light, carry the story of extreme gravity across billions of years and billions of kilometers. And yet, even with all we know, there is mystery. What truly happens at the center of a black hole, beyond the event horizon, where density becomes infinite and equations lose meaning? Does space end there? Or does it transform into something else, a region governed by quantum gravity, where space-time itself is quantized? The answers remain hidden, locked away behind a curtain that no signal can cross. Still, through observation and mathematics, we approach its edge. We see how light curves near these cosmic abysses, how time slows, how matter glows and falls. Each discovery brings us closer to understanding the architecture of the universe. For to know gravity in its purest form is to glimpse the framework of everything from the fall of an apple to the birth of a star. The deeper we look, the more we realize that extreme gravity is not an enemy of order, but its sculptor. It shapes galaxies, binds planets, and defines the rhythm of cosmic evolution. To follow its trail is to journey to the heart of what space and time truly are. And so, to grasp its nature completely, we must descend closer still, not into the black hole yet, but to the surface of its gentler sibling, the neutron star, where matter stands on the threshold of the impossible and light itself hesitates before leaving. To descend toward a neutron star is to approach a world that bends every rule of common experience. From a distance, it appears deceptively small, a faint point of light hidden in the dark. But as one draws closer, its gravity begins to shape perception itself. The space around it curves so sharply that what lies behind comes into view. Stars on the far side bend into sight, stretched into ghostly arcs. Time seems to stretch as the gravitational field deepens, each second lengthened by the star's immense pull. The universe beyond appears to speed up, while one's own motion slows. This is not illusion, but geometry. The warping of space-time near a neutron star changes the way everything behaves. Particles that once moved freely now spiral inward, following paths determined not by any force, but by the shape of the cosmos itself. Even light, which travels always in straight lines, finds those lines distorted. It bends not because it chooses to, but because space bends beneath it. The closer one moves, the stranger the world becomes. The surface, if it can be called that, is the last place where matter remains matter. Below it, the distinction between particle and field begins to blur. The crust is composed of atomic nuclei, locked in a lattice so dense that a single cubic centimeter weighs more than a mountain. Beneath that, the pressure is so intense that electrons and protons fuse into neutrons, creating a fluid that behaves like a single quantum object. It is neither solid nor liquid, but something beyond those categories. A state of matter that can only exist where gravity's grip is absolute. The gravity at the surface is roughly 200 billion times stronger than that of Earth. To resist that pull, one would need to move upward at nearly half the speed of light. Even light itself escapes only after losing much of its energy, its frequency stretched by redshift until it fades into invisibility. This immense pull means that no atmosphere can exist. The star is bare, its surface a glowing crust of nuclear iron, constantly radiating heat left over from its violent birth. If we could observe this world from above, we would see something haunting and serene. The horizon would curve away sharply, and because of space-time's distortion, more than half the sphere would be visible at once. The sky would not be black but distorted, filled with arcs of light bent from distant stars. A step in any direction would feel like falling, for every direction points inward toward the dense core. The physics here are governed not only by Einstein's relativity but also by quantum mechanics. The neutrons packed inside resist compression due to the Pauli exclusion principle, a law that forbids identical particles from occupying the same state. This resistance is the only thing preventing total collapse. Gravity, relentless and eternal, pushes inward, while quantum pressure pushes back. Between these opposing infinities, the star finds a fleeting balance. It exists as an equation realized in matter gravity and quantum law joined in perfect tension. But this balance is fragile. Add a little more mass, and even quantum pressure cannot hold. The neutrons themselves begin to merge, and the collapse resumes. Space folds further. Time slows more, and the threshold of no return forms the event horizon. The neutron star becomes a black hole, and the last barrier between existence and oblivion vanishes. Even so, the geometry near the neutron star gives us a glimpse of what lies beyond. The way time slows, the way light bends, and the way energy radiates all echo what happens near a black hole, though not yet to infinity. In studying neutron stars, we study the approach to that final boundary. Every pulse from a rotating neutron star carries information about how space-time behaves under immense strain. Each photon that escapes tells of the tug between gravity and light, between curvature and energy. Einstein's equations predict these effects precisely, and observations confirm them. The timing of pulsars is so exact that they serve as cosmic clocks, measuring the ripples of space-time caused by gravitational waves passing through the galaxy. When two neutron stars orbit each other, their signals reveal how gravity drains energy from the system, drawing them ever closer. And when they finally merge, detectors on Earth feel the faint tremor of that union, a whisper from the far reaches of space, confirming the geometry Einstein described a century ago. Gravity, in these extremes, becomes more than a property of mass. It becomes a storyteller, carrying the memory of collapse and the promise of understanding. Every star that dies, every neutron that resists, every photon that struggles to escape, tells part of the same tale, the tale of how space and time are intertwined. To follow this story further, one must cross the final threshold and confront the place where gravity rules without limit, where even light surrenders to curvature. There, beyond any surface or matter, lies the event horizon, where gravity wins absolutely, and space-time becomes its own shadow. To approach the event horizon is to step beyond ordinary meaning. In the region where a neutron star's curvature deepens toward infinity, the distinction between inside and outside begins to blur. The rules that govern matter still apply just above the threshold, but they begin to lose their precision. Imagine moving toward an invisible boundary where light itself slows, where every photon that tries to leave is dragged back by the slope of space-time. For a distant observer, nothing ever quite crosses. The falling object appears to fade and freeze, its image stretching into red and then vanishing. Yet from the object's own point of view, the crossing is swift, unremarkable, and irreversible. This paradox is the essence of extreme gravity. Time behaves differently for different observers. From far away, the event horizon is an eternal border. For the one who falls, it is a moment in time. Both descriptions are true because time is not absolute. Each frame of reference writes its own version of reality, and gravity is the editor that reconciles them. In this sense, the black hole does not destroy information. It hides it behind geometry. What that geometry ultimately does with the information remains one of the great mysteries of physics. The neutron star, by contrast, offers a glimpse of this realm without yet crossing the limit. It is a model of resistance, an object that has found a way to exist on the edge of collapse. The curvature near its surface is so sharp that even modest changes in density would trigger the same endless descent that creates a black hole. The balance between gravity and quantum pressure is so delicate that adding a single % of mass could destroy the equilibrium entirely. The star would shrink by centimeters and then vanish behind an event horizon, leaving no trace of its former surface. In the decades since, Einstein's theory reshaped our understanding of the cosmos. Observations have confirmed these predictions with breathtaking precision. The bending of starlight by the sun during an eclipse, the slowing of time near massive bodies, the orbital decay of binary pulsars, radiating gravitational waves, all align perfectly with the mathematics of curvature. The neutron star and the black hole are not abstractions. They are living confirmations of the geometry that defines reality. When two neutron stars orbit each other, the system becomes a dance of gravity so precise that it serves as a laboratory for testing relativity itself. Their mutual attraction emits ripples through space-time gravitational waves that stretch and compress the very distance between objects as they pass. These waves travel outward at the speed of light, carrying information about the motion, the mass, and the curvature of their source. When such waves were first detected on Earth, the universe proved that space-time is not static. It is a dynamic fabric, capable of vibration. The difference between the neutron star and the black hole is thus not one of kind, but of completeness. Both curve space-time, but one stops short of total collapse. The neutron star still lets the universe look upon it. The black hole hides its truth behind a horizon. The neutron star radiates the energy of resistance, while the black hole radiates only silence, or perhaps, as Hawking revealed, a faint whisper of quantum light leaking from its edges. This faint emission, known as Hawking radiation, suggests that even a black hole is not truly eternal. Over vast timescales far longer than the current age of the cosmos, it will evaporate, losing mass photon by photon, until it vanishes completely. What remains then? Perhaps only the memory of curvature, perhaps nothing at all. The mathematics is clear, but the meaning is not. Both objects show us the limits of understanding. The neutron star reveals what matter becomes when pushed beyond atomic structure. The black hole reveals what happens when gravity itself becomes structure. Between them lies the full spectrum of physical law, quantum mechanics on one side, general relativity on the other. Where they meet, theory falters, and a new physics waits to be discovered. To explore that meeting point, we must imagine not from afar but from within. To stand upon the surface of a neutron star is to stand at the boundary of the possible. It is there, where gravity and quantum law share equal command, that the nature of extreme gravity reveals itself most clearly. The next step in this journey is not to observe from a distance, but to descend to imagine what it means to exist in a place where every atom is crushed, where the air is made of neutrons, and where the pull of the universe itself becomes a wall. That is where the next truth begins to form. On the very surface of the densest object, matter can create before falling into the darkness forever. To imagine standing on a neutron star is to abandon every familiar sense of scale. It is a world where the word heavy loses meaning. Gravity is not a gentle pull, but an all-encompassing descent, a command written into the structure of space-time itself. If one could hover somehow above its surface, the very act of approaching would stretch time. The closer you draw, the slower your seconds would pass compared to those far away. From a distance, you would appear frozen, caught in an eternal moment, as light from your descent struggled to escape the star's immense gravity. A neutron star is small enough to fit within the boundaries of a great city, yet holds the mass of 1 or 2 suns. Its surface gravity is about 200 billion times that of Earth. To drop an object from a single meter above the crust would accelerate it to nearly half the speed of light before impact. Nothing solid could survive such a fall. Even the act of standing is impossible. There is no material known or imagined that could resist that force. Every molecule, every atomic bond would be crushed into its constituent particles. The crust beneath your imagined feet is made of atomic nuclei, so tightly packed that they behave more like a solid lattice of metal than any rock or mineral. It is only a few centimeters thick, yet it bears the weight of a whole star. Beneath it lies a sea of neutrons, compressed into a superfluid, a quantum ocean that flows without friction, obeying laws that defy ordinary experience. Within that ocean, individual particles lose their identity. They merge into a single coherent state, like notes blending into one perfect tone. If you could look outward from that impossible surface, the view would defy logic. The star's gravity bends light so sharply that you could see the entire surface at once. The far side, curving up into view, as though space itself folded around you. The sky above would not be dark, but filled with distorted arcs of starlight, drawn into luminous rings. Every motion, every step, every thought would occur more slowly compared to the universe beyond. Minutes on this surface could be hours for someone far away. The temperature of the star glows near 1,000,000 degrees Celsius, though its light is faint and red when seen from space. The radiation that escapes carries the story of its past. The collapse of a giant, the fusion of its heart, and the birth of this dense remnant. Each photon must climb out of a gravitational well so deep that it loses much of its energy before escaping. By the time it reaches the open void, its color has shifted, its strength diminished, but its message remains. Matter has reached its final form. The magnetic fields of a neutron star are colossal. They can be trillions of times stronger than Earth's. These invisible lines of force twist around the star, trapping charged particles and hurling them outward at nearly the speed of light. The poles become beacons, emitting narrow cones of radiation that sweep through space like the beams of a lighthouse. When one of those beams crosses Earth, we detect a pulse, a rhythmic signal of astonishing precision. Each pulse marks the rotation of the neutron star, some spinning hundreds of times each second. These are pulsars, the ticking clocks of the galaxy. Their precision is so great that they rival atomic clocks. Astronomers use them to measure time, to test relativity, to detect the faint ripples of gravitational waves passing through the cosmos. Each tick is a reminder that even in death, a star can still mark the rhythm of the universe. Yet the same precision that defines their motion also marks their decay. Slowly, over millions of years, pulsars lose energy. Their spin slows, their light fades, and they drift towards stillness. Eventually the pulses cease, leaving only a silent sphere of cold, dense matter, a remnant too faint for any telescope to find. The surface of a neutron star may seem the final frontier of matter, but it is also a doorway to deeper mysteries. The forces that hold it together, gravity, electromagnetism, the strong nuclear interaction, reach perfect balance here. Every proton, every neutron, every particle obeys laws stretched to their limit. To study such an object is to see nature's equations written in their purest form. No laboratory on Earth can replicate these conditions. The neutron star is the ultimate experiment, conducted by the universe itself. If you could peel away its layers, you would find zones stranger than any dream. Near the surface lies the solid crust of nuclei. Beneath it, the neutron fluid. Deeper still, perhaps an ocean of quark matter, a place where neutrons dissolve into their most fundamental parts. There, quarks roam freely, no longer confined into protons and neutrons. It is possible that inside the densest neutron stars, this quark soup already exists, a whisper of the early universe frozen into a star. And still, Gravity holds it all in place. The balance remains fragile. Add just a little more mass, and the whole structure collapses. The neutrons lose their final resistance, and space-time folds into the darkness of a black hole. For a moment, the star's magnetic fields flare. Its final energy bursts outward, and then it vanishes. Where once was matter now exists only a region from which nothing can return. Yet even on the edge of such annihilation, beauty persists. The neutron star shines, not with the brilliance of fusion, but with the endurance of gravity's will. It is the universe's declaration that even death can produce order. Every pulse of light, every burst of radiation, every curve of space-time around it is proof that the laws of physics remain faithful, even in the most extreme conditions. To stand, even in imagination, on such a world is to feel the unity of all things, the fall of gravity, the resistance of matter, the slow bending of time. It is to witness the frontier where space becomes dense, where motion becomes meaning, and where the universe reveals its strength, not through destruction, but through perfect, relentless balance. From this surface, one can almost sense the pull of something greater still, a realm where no balance remains, where gravity takes its final victory, and light itself can no longer escape. To linger above a neutron star is to dwell on the edge of comprehension. The mind strains to hold the scale of its gravity, the closeness of its matter, the silence of its power. Everything familiar fails here. The distinction between weight and energy dissolves, and the difference between space and time begins to blur. What was once a simple idea of down becomes meaningless, for every direction points toward the same crushing center. If we could float a few kilometers above this surface, the star beneath would seem to fill almost the entire sky. The curve of space-time would bend the image so completely that even the far side of the star would appear at once, wrapping the horizon in a luminous band. Light that escaped upward would take twisted paths, spiraling and looping before finally breaking free. To watch it would be to see the universe through a lens carved by gravity's hand. And if we could look outward from that place, the distant stars of the galaxy would appear faint and distorted. Their light, slowed by the star's gravity, would shift to lower energy, stretching into deep red. Time itself would crawl. A single heartbeat near the surface might correspond to many heartbeats for someone far away. Communication between those two worlds would falter, one sending signals that grow fainter and slower, the other receiving them as echoes from another age. Yet, amid this distortion, the neutron star remains a stable object, a quiet monument to balance. Its crust is stronger than any material known, able to resist forces that would tear ordinary atoms apart. Beneath it lies a sea of neutrons that behaves like a single quantum fluid, rotating as one immense particle. Scientists call this superfluidity, a state in which friction vanishes and motion can continue forever without decay. The entire star may spin in perfect synchronization, its surface and core bound together by quantum law. As it spins, its magnetic field cuts through the surrounding space, dragging charged particles into spirals of acceleration. These particles emit radiation across the spectrum: radio waves, visible light, X-rays, even gamma rays. The beams from its magnetic poles sweep through the cosmos, each rotation sending a flash across the galaxy. When these beams pass by Earth, we detect them as precise pulses, arriving with such regularity that they reveal the rotation of the star down to microseconds. Each pulse is a whisper from an ancient collapse, a steady rhythm born of catastrophe. The time between pulses changes slightly as the star emits radiation and loses energy, its rotation slowing ever so gradually. Over thousands of years, the once furious spin gentles. The pulses fade, but their memory remains imprinted in the cosmos, a record of the transformation of energy into order. The mathematics that describe this process are unrelenting. Every rotation radiates energy through electromagnetic waves and gravitational ripples, stealing angular momentum from the star. The loss is minute but constant. Over eons, the star cools, darkens, and spins more slowly, becoming first a dim X-ray source, then a quiet relic. Even in stillness, its mass remains, an unyielding knot of matter, marking where a giant once lived. Neutron stars remind us that the universe preserves nothing easily. Even balance is temporary. The pressure that sustains these stars comes from quantum mechanics itself, from the refusal of neutrons to share the same state. This degeneracy pressure halts gravity just before collapse, but only for a while. As the star cools and loses energy, the balance shifts. In the most massive neutron stars, the slightest change, a tiny increase in mass, from accreting nearby matter, or the decay of particles deep inside, can tip the scale. When that moment arrives, the equilibrium ends. The crust shatters in silence. The star collapses inward once more. Its mass crosses the critical threshold, and no law of physics can prevent the final fall. The event horizon forms, and the star becomes a black hole. The light that once pulsed outward ceases forever, replaced by a darkness that hides all motion. Yet not every neutron star meets this fate. Some endure for billions of years, cooling slowly into invisibility, still spinning quietly in the dark. They are relics of creation, fossils of gravity, reminders that the laws of physics can hold even against their own destruction. Their magnetic fields, though weakened, persist, extending far into space. Occasionally, a passing particle or a remnant disk of matter will strike the surface, releasing a brief flare of radiation, a last flicker from a sleeping titan. The study of neutron stars has reshaped the way we see the cosmos. Through them, we measure the warping of space-time, the strength of magnetic fields, and the limits of quantum matter. Every observation reveals the unity of physical law. The same equations that describe subatomic particles also describe these cosmic giants. In their depths, the smallest and the largest scales meet. And perhaps most profound of all, neutron stars show us that gravity, even when fierce beyond measure, can coexist with order. They are the boundary markers of the possible, the last standing structures before the descent into the unknown. To understand them fully is to stand on the threshold between two realities, one governed by the physics we know, the other by what still waits to be discovered. From this threshold, there remains only one direction left to look. Beyond the realm of surfaces and solids lies the domain where gravity accepts no balance, no light, no escape. The journey now turns toward that frontier, the event horizon where space itself surrenders, and the universe reveals its most absolute form. To take the final step down to a neutron star's surface would be to confront gravity in its purest form. Every motion, every vibration of air, every atom's spin would be slowed by time dilation. The moment of descent would feel infinite. For an outside observer, the approach would appear to last forever, the traveler frozen just above the surface as the redshift deepens and light struggles to climb free. Yet for the traveler, the fall would be swift, irresistible, over before a heartbeat could begin. This is the paradox of gravity taken to its limit. It does not merely pull, it reshapes time itself. Near a neutron star, space-time curves so tightly that the shortest path through it no longer feels like movement through space but through duration. The weight of existence is not just physical, but temporal. The star's immense density bends every law, every constant, every intuition, born of gentler worlds. If the crust could be touched, it would not feel like metal or stone. It would feel like nothing the senses can imagine. The pressure beneath each footstep would exceed the force that binds atomic nuclei. A fraction of a second's contact would vaporize any substance, not by heat, but by sheer gravitational compression. Even the strongest material conceived by human science would fail instantly. The act of standing is not possible here. The neutron star allows no witness. And yet, in imagination, we may still observe. The landscape stretches smooth and lifeless, a featureless plain of dark iron, glowing faintly with the residual heat of its birth. Above it hangs a sky warped into impossible shapes. The horizon curves upward. The far side of the star glimmers above the edge, reflected by the bent geometry of light. There is no true night, no true direction. The idea of up or down has lost meaning. The silence here is not emptiness, but compression. Sound cannot travel because there is no air, only a thin layer of plasma, bound by gravity's leash. The only motion is the star's rotation, a slow turning that drags its magnetic field through the void. Charged particles caught in those lines spiral outward, creating waves of radiation that sweep across the galaxy. These beams of light and energy mark the rhythm of a dead star's heartbeat, precise enough to measure the drift of time itself. As the star spins, the outer crust occasionally cracks. Tremendous stresses build up as the magnetic field twists and the solid lattice beneath strains against it. When it finally yields, the quake releases more energy in a millisecond than 1,000 nuclear explosions. Astronomers detect these as bursts of X-rays or gamma rays, brief flashes from deep space. These events are reminders that even a dead star can still move the cosmos. Within the core, the story continues unseen. The superfluid ocean of neutrons flows in perfect harmony, rotating as a single entity. But sometimes, as the crust shifts, it slips slightly against the interior. This sudden adjustment transfers angular momentum, causing the star's rotation to speed up by an almost imperceptible amount. Astronomers call these glitches, tiny jumps in the star's spin. They are the echoes of internal forces still struggling for balance after a billion years of calm. Such a world, though silent, is anything but static. Its gravitational field interacts with everything around it, bending the paths of passing particles and curving light from distant stars. If a spacecraft were to orbit a neutron star, its motion would be a delicate dance of precision. Even a small deviation could send it plunging toward the surface, where tidal forces would tear it apart long before impact. The difference in gravity between its upper and lower sides would stretch it into fragments, scattering it as plasma across the star's magnetic field. And yet, from the safety of distance, the neutron star is beautiful. Its light, faint and red, still carries the memory of the supernova that created it. Its magnetic field, invisible yet immense, sculpts the space around it into elegant arcs. Its gravity, though monstrous, shapes order out of chaos, pulling debris into perfect orbits, or funneling matter into radiant jets. The neutron star is gravity's masterpiece, a portrait of restraint painted at the edge of annihilation. It shows that the universe can hold its breath, balancing infinite pressure against infinite compression for billions of years. But this balance cannot last forever. Sooner or later, energy fades, temperature falls, and motion ceases. When the last heat leaks away and the magnetic fields decay, the neutron star becomes an invisible cinder of space-time, a relic of perfection preserved by gravity alone. From here, the journey deepens into the final domain of gravity, where no surface remains, no balance survives, and time itself bows to curvature. To cross from the neutron star to the black hole is to leave behind the last remnant of matter and enter the geometry of the infinite. There, beyond the reach of light, gravity is no longer something that shapes the universe. It becomes the universe itself. There comes a point when gravity no longer negotiates. When a collapsing star passes the threshold that separates resistance from surrender, all that remains is descent. Matter folds inward upon itself, and space-time, unable to bear the strain, gives way. What is born from that collapse is unlike anything else in the universe, a black hole, an object without surface or substance, defined only by geometry. At first glance, a black hole seems impossible. How can something exist that has no physical boundary, no material body, and yet possess the weight of suns? Yet Einstein's equations demand it. When mass becomes sufficiently concentrated, the curvature of space-time grows so steep that all paths lead inward. Even light, moving at 300,000 kilometers per second, cannot escape. The edge of this region is the event horizon, a boundary not made of matter, but of destiny. Imagine falling towards such a place. From far away, the black hole appears unremarkable, a dark sphere set against the stars. But as you draw near, the scene begins to twist. Light from the background bends into arcs, forming a glowing ring that encircles the shadow. This halo is not the black hole itself, but the image of all light that narrowly escaped its pull. What lies within the shadow is hidden forever, sealed by the rules of space-time. The event horizon is not a surface in the traditional sense. It has no texture, no temperature that can be felt, no resistance to touch. It is simply the point where the geometry of space-time turns inward completely. Once crossed, every possible path, through time and space, leads only deeper. There is no turning back, no path of escape, not even for light, which follows the curvature perfectly. From a distance, the fall into a black hole appears to slow endlessly. The traveler's image fades, stretched and redshifted, until it disappears into darkness. Time, as seen by the distant observer, halts at the horizon. Yet for the traveler, time continues smoothly. They cross the horizon in an instant, feeling no sudden change. The world outside accelerates into infinity as their own path carries them toward the singularity. In this way, both perspectives are true, each shaped by its own frame of reference. Inside the horizon, the concept of direction reverses. In the same way that every path through time moves forward, every path through space now leads toward the singularity. Falling inward is no longer a choice, but a law. Space itself flows inward, faster than light can move outward. The horizon is not a wall that traps light. It is a current in space-time that carries it inward faster than it can escape. At the center, if the equations hold, lies the singularity, a point of infinite density, where the curvature of space-time becomes infinite. Here, Einstein's theory reaches its limit. The equations no longer describe reality, because reality itself dissolves into something beyond our comprehension. Whether the singularity truly exists as a point, or as a region governed by quantum gravity, remains unknown. It may be that at such scales, space and time lose their meaning entirely. The black hole is defined by only three measurable properties: mass, charge, and spin. Every other detail of the star that created it, its composition, its magnetic field, its history, is erased. This is the meaning of the phrase that physicists call the no-hair theorem. Black holes have no distinguishing features beyond these three numbers. They are pure geometry, stripped of individuality. Yet even in their simplicity, black holes are not empty. The region around them teems with energy. Matter that drifts too close does not fall directly inward, but spirals, forming an accretion disk, heated by friction to millions of degrees. This disk glows with X-rays and gamma rays, emitting more energy per gram than any other process in the universe. Some of this matter is flung outward at near light speed, forming jets that pierce through galaxies. Paradoxically, the darkest objects in the universe are also the brightest engines of light. What we call infinite gravity is not truly infinite pull, but infinite curvature. The strength of gravity near the event horizon is finite, determined by the mass of the black hole. A supermassive black hole at the center of a galaxy may have gravity at its edge weaker than that on a neutron star. It is the structure of space-time that is extreme, not the force itself. The difference lies in scale. A small black hole's horizon sits close to its singularity, creating violent gradients of gravity that would tear any object apart. A giant black hole's horizon lies so far out that a traveler could cross it without noticing, drifting quietly into the dark before the pull grew unbearable. This boundary, this horizon, defines the universe's most absolute law. It is the edge beyond which the concept of observation ceases. Information, light, and cause itself are confined within. The event horizon is the frontier where knowledge ends. For all the power of telescopes, equations, and thought, we can never know what lies within directly. The black hole is both a mystery and a mirror. It reflects the limits of our understanding as clearly as it hides its own truth. And yet, we have seen them. In 2019, the Event Horizon Telescope revealed the first direct image of a black hole's shadow in the galaxy Messier 87. The ring of light surrounding its dark core matched the predictions of Einstein's equations to exquisite precision. In that image, humanity glimpsed the curvature of space-time itself, captured not by imagination, but by observation. Black holes are not cosmic errors. They are natural consequences of gravity carried to its logical extreme. They shape galaxies, influence star formation, and drive the engines of quasars that light the distant universe. Far from being dead zones, they are architects of creation, their gravity sculpting the structure of everything that surrounds them. To understand the black hole is to understand the victory of gravity, not as destruction, but as transformation. What begins as collapse ends as curvature. Matter becomes geometry, and energy becomes space. The black hole is not an abyss, but a continuation of the same law that binds the planets, that shapes the stars, that holds us to Earth. It is gravity brought to perfection. And just as the neutron star revealed the edge of matter, the black hole reveals the edge of space itself. Beyond it lies no further descent, no deeper well. There is only the horizon, the place where gravity wins, and where the universe, in silence and symmetry, folds into itself. To drift closer to a black hole is to enter a realm where the universe changes its language. Geometry replaces force, and light itself becomes a prisoner of curvature. From far away, the region seems quiet, the blackness serene. Yet the stillness is an illusion. Every photon, every grain of dust, every fragment of gas that dares to approach is caught in an endless spiral. Motion becomes destiny. The first sign of this change is the distortion of light. The sky bends. Stars that once formed familiar constellations now smear into luminous rings. Their light, stretched by gravity, grows redder and fainter as it climbs the steep slope of space-time. The black hole's outline begins to dominate the view, a perfect sphere of darkness surrounded by a halo of burning matter. This glow is the accretion disk, a swirling storm of gas and plasma heated to millions of degrees as it falls inward. In that disk, the universe performs one of its most violent dances. Friction between particles, driven by magnetic turbulence, transforms gravitational energy into heat and radiation. The gas moves at nearly the speed of light, circling the horizon in endless loops before finally vanishing. In those final orbits, time slows so dramatically that an outside observer would see the motion freeze, each particle suspended on the edge of disappearance. But the light it emits still escapes, painting the darkness with a faint, persistent fire. For the material within the disk, the story is different. Time flows normally along its path. The gas feels no sudden change as it crosses the horizon. It simply continues to fall, following space-time's geometry. There is no sensation of impact, no resistance, no barrier. The black hole does not crush matter at its surface, because it has no surface. Instead, it absorbs the very concept of location. Inside, space and time trade places. What once was a direction in space becomes a direction in time, and the future points only toward the singularity. A small black hole creates the most dramatic version of this journey. Its horizon lies only a few kilometers across, yet its mass may exceed several suns. The gradient of gravity, the difference in pull between one side of an object and the other, is immense. A body falling toward it would experience spaghettification, stretched into a thread of atoms as the gravity at its feet exceeds that at its head. The body would elongate, thin, and dissolve into plasma long before crossing the horizon. The black hole consumes not by crushing but by stretching, unraveling matter into energy. Supermassive black holes, by contrast, are gentler at the edge. Their horizons span millions of kilometers, and the tidal forces there are weak enough that a spacecraft could cross unharmed. For a while, the traveler would drift through darkness, surrounded by the faint glow of the accretion disk and the distorted image of the universe. Time would pass normally inside the ship, though billions of years might elapse outside before the traveler reached the singularity. To fall into such a black hole is to move forward in time as far as the universe will allow. In theory, the path continues to the singularity, a point where all known physics fails. At that center, density and curvature grow without limit. But many physicists believe the singularity is not a true point. Instead, it may be a region where quantum gravity takes over, replacing infinity with something finite but strange. Some theories suggest that within that region, space-time could loop back on itself, or even connect to another universe. If so, a black hole might not be an ending at all, but a passage, though one no traveler could survive to tell. To the outside world, the black hole remains perfectly silent. It gives no hint of what happens beyond the horizon, yet it influences everything nearby. Its gravity binds stars into orbit, drives the growth of galaxies, and shapes the evolution of the cosmos. The centers of galaxies, including our own, hold supermassive black holes that weigh millions or billions of times as much as the Sunday sun. Around them, entire systems of stars move in complex harmony, drawn by an unseen hand. Despite their secrecy, black holes are not truly invisible. The matter that orbits them shines with furious energy. When a black hole feeds on gas or stars, the infalling material releases a fraction of its mass, as light a process far more efficient than nuclear fusion. Quasars, the brightest objects in the universe, are powered by black holes feeding on their surroundings. For a time, each one can outshine all the stars in its host galaxy combined. The interplay between darkness and light defines the paradox of the black hole. It is both the most efficient engine and the perfect absorber, both creator and destroyer. It is gravity's triumph made visible, a region where mass, energy, and space become one expression of the same law. And though nothing escapes its grasp, the universe itself owes much of its structure to these silent giants. Even so, mysteries remain. If information cannot escape, how does the universe preserve the laws of quantum mechanics, which forbid its destruction? The black hole information paradox, as it is called, remains one of the deepest puzzles in physics. Stephen Hawking's discovery of quantum radiation leaking from the horizon hints that black holes may eventually evaporate, releasing their secrets slowly over time. But whether the information survives that process or is truly lost is still unknown. The event horizon stands as the most profound boundary in nature, not a wall of matter, but the limit of knowledge. It marks the place where observation ends and imagination must begin. Beyond it, space folds into mystery and time flows toward a singular destiny. Yet even in that darkness, the laws of physics continue their work, silent and exact. The black hole is not an anomaly, but a natural outcome of those laws carried to completion. It is the universe, closing a circle upon itself. From this horizon of no return, the next question arises naturally. How does space-time behave in the regions just outside, where light can still escape, but time slows and bends? What happens to the flow of existence when gravity nears its ultimate strength? To answer, we must look not only into the depths of the black hole, but into the ways it warps everything around it. The bending of light, the slowing of clocks, the stretching of signals. It is there, in the warping of space and time, that the universe reveals the full power of gravity's design. To linger just outside a black hole's event horizon is to exist on the very edge of time itself. The closer you move, the more the rhythm of the universe changes. Faraway stars appear to drift faster, their light flickering with an unnatural pace, while your own heartbeat slows. Every second you experience stretches into eternity for the rest of the cosmos. The laws of relativity are no longer background truths, they become the air, the ground, the rhythm of existence itself. From this vantage, the event horizon seems to shimmer, not because it emits light, but because the space around it glows. The accretion disk burns with heat beyond comprehension, each fragment of matter releasing its mass as radiation before vanishing from the visible world. The closer it comes to the horizon, the more its light is dragged forward in time, stretched into longer wavelengths, dimming as it escapes. To the distant eye, the fall appears to slow, each particle frozen in a final moment that never ends. But for the matter itself, the crossing is immediate. Time is not the same for both observers. Gravity does not bend it evenly, it reshapes it according to position and motion. The curvature here is total. Space bends inward so sharply that even light emitted sideways curves back. The horizon marks the boundary where that curve becomes infinite, where all possible trajectories lead toward the singularity. This is what no escape truly means, not a wall or a force, but a geometry that folds every path into itself. If one could hover impossibly close, without falling in, the view of the universe would be surreal. The entire cosmos would be compressed into a narrow halo of light. Time beyond would seem to race forward. Stars would live and die in an instant. The flow of the galaxy would pass like a breath. The observer near the horizon would remain suspended, witnessing eternity in moments. And yet, within this strangeness lies order. The equations of general relativity describe every curve precisely. The gravitational field obeys the same logic that governs a falling apple. It is the same law extended to its absolute conclusion. Gravity does not change its nature near a black hole. It only reveals the full scope of what it has always been, the shape of reality. The black hole's rotation adds another layer to this geometry. A spinning black hole drags space-time around with it, twisting the surrounding region into a whirling funnel. This phenomenon, called frame dragging, means that nothing nearby can remain still. Even light is caught in the rotation, forced to swirl around the hole before it can escape. The boundary between the rotating region and still space is called the ergosphere. Within it, energy can be extracted from the black hole's spin. The process, first described by Roger Penrose, allows a particle to enter, split, and send one fragment deeper inward, while the other escapes with more energy than it had before. From the darkness, motion creates light. This twisting of space-time blurs the distinction between gravity and energy. The black hole's spin can power colossal jets that stream outward from its poles, stretching for thousands of light years. These jets are not formed by matter escaping the black hole itself, but by magnetic fields, channeling the energy of rotation. They pierce through interstellar space like cosmic spears, carrying the signature of the event horizon to distant galaxies. Even at this scale, the black hole remains precise. Every orbit, every photon, every ripple of radiation follows the paths dictated by curvature. The region around the horizon becomes a lens, bending light into perfect arcs. It magnifies distant stars, turning the black hole into a window rather than an end. What seems like destruction is, in truth, an instrument of clarity. Through these distortions, we glimpse the true nature of space. For all its mystery, the black hole is not chaos. It is order expressed at a scale that overwhelms the senses. Its shape is pure mathematics, made visible. The laws that govern it are the same laws that guide the moon around Earth and light through glass. The difference is only in degree, in the total devotion of space and time to the weight of gravity. When we speak of infinite gravity, we do not mean an infinite force pulling inward. The gravitational field at the event horizon depends only on the mass and size of the black hole. A large one, such as the monster at the center of our galaxy, would exert a surprisingly gentle pull at its horizon, far weaker than that of a neutron star's surface. What is infinite is not the strength but the curvature, the way space-time folds and continues without end toward the singularity. The event horizon itself is a paradox made of precision. It is not a place that can be seen directly, but its shadow is measurable. The light that grazes its edge reveals its shape. The image captured by the Event Horizon Telescope was not of the whole, but of its influence. The glowing ring of photons orbiting the void before surrendering to it. In that photograph, humanity saw the silhouette of geometry itself, a shadow cast not by matter, but by the bending of reality. To stand at this frontier, even in thought, is to recognize that gravity has completed its work. Matter has ceased to be matter. Space has ceased to be neutral. The universe folds inward, and time flows one way only. The event horizon is where the story of collapse reaches its conclusion, not an end in destruction, but in transformation. Beyond it lies silence, and within that silence, perhaps, the next great mystery. The black hole's existence demands a new physics, one that unites the quantum and the cosmic. Somewhere in that hidden region, where gravity and probability intertwine, lies the answer to what the universe becomes when space and time themselves are consumed. From here, we turn to what happens just outside this threshold, to the warping of light and the slowing of time that reveal the fingerprints of gravity itself. For to understand a black hole or a neutron star is not merely to observe their shapes, but to feel the rhythm of their influence, the way they stretch existence. In the dance of light and time near their edges, the universe reveals the art of gravity made visible. Gravity is not merely a force that draws objects together. It is the shape of existence itself, the curve of space, and the rhythm of time. In the presence of great mass, both bend and slow. The stronger the gravity, the deeper the curve, and the slower the clock that measures it. What we experience as weight is the faintest whisper of that bending, a tiny echo of a geometry that, near the edge of a black hole or a neutron star, becomes absolute. To understand the nature of gravity is to understand that time itself is elastic. In Einstein's universe, clocks do not all agree. Those near a massive object run more slowly than those far away. This is not a mechanical failure or illusion. It is reality. Time's flow depends on where it moves through space-time. The deeper you are in a gravitational field, the slower your seconds unfold compared to those in the open void. Near a neutron star, this difference is profound. If a clock were placed upon its surface, its ticking would slow dramatically. For every second that passes there, several might pass for an observer far from the star. This is gravitational time dilation, not a trick of perspective, but a property of space-time itself. The star's immense density bends time the same way it bends light. What is astonishing is that these predictions, once only equations, have been confirmed. Satellites orbiting Earth must adjust for time dilation to keep global positioning systems accurate. The difference near a neutron star is not tiny, but colossal. Imagine hovering above such a star and watching a beam of light escape from its surface. The beam begins bright and blue-white, but as it climbs through the gravitational well, it loses energy. Its wavelength stretches, shifting toward red, until by the time it reaches the distant observer, it glows faintly, almost invisible. This redshift is gravity's fingerprint upon light. The same effect happens near a black hole, where the shift becomes so extreme that light fades entirely, trapped in time as much as in space. If we could watch an object fall toward a black hole, we would see it slow and dim, never quite crossing the event horizon. Its signals would take longer and longer to reach us, their frequencies stretching toward infinity. To the falling object, though, nothing strange would occur. It would pass the horizon without pause, while the universe outside would seem to accelerate toward its end. In this meeting of perspectives lies the essence of relativity. Every observer experiences time and motion according to their own path through space-time. There is no single now that binds the cosmos. The bending of light reveals the same truth in another form. When light passes near a massive object, it follows the curve of space-time, bending as though deflected by a lens. This effect, known as gravitational lensing, allows distant galaxies to be magnified and multiplied by the mass of those in front of them. Through these cosmic lenses, astronomers can see objects billions of light-years farther than would otherwise be possible. Each arc and smear of light across the sky is a signature of curved space, a message from gravity written in luminous script. The same curvature governs orbits and paths. A planet moves not because it is pulled, but because it follows the straightest possible route through curved spacetime. Around Earth, these curves are gentle. Around a neutron star or black hole, they become extreme. The path of a photon can loop completely around the object before escaping, creating rings of light known as photon spheres. To an observer, these appear as halos of fire surrounding darkness, the visual echo of spacetime's geometry. In these regions, time and space lose their separate meanings. To move through space near a massive object is also to move through time. The faster one moves, or the closer one comes to gravity's source, the more intertwined the two become. At the event horizon, this union is complete. All directions in space lead toward the future in time, and that future points inward. There is no path backward, no return to the past, only the inevitable continuation into the singularity. The distortion of time is not confined to black holes. Even on neutron stars, time flows differently across their small surfaces. The poles and the equator experience slightly different gravity due to rotation and shape, leading to minute differences in the passage of time. The star's intense magnetic fields further complicate this rhythm, affecting the motion of charged particles and the emission of light. Every pulse of radiation, every beam that sweeps across the galaxy, carries the subtle influence of time dilation in its signal. It is humbling to realize that this same principle touches us. Though Earth's gravity is mild, time at sea level runs slightly slower than time on a mountaintop. Every human lives within a personal distortion of space-time, too small to notice, but mathematically exact. In the vastness of the universe, these small distortions accumulate, shaping the structure of galaxies, the life of stars, the evolution of everything that exists. To watch the stars and measure their bending light is to read the shape of time itself. The lensing of galaxies, the slowing of pulsars, the redshifting of radiation, all reveal the hidden architecture that binds the cosmos together. Gravity, once thought to be a simple attraction, is revealed as the grand geometry of being. The deeper we explore this geometry, the more we see its unity. The same equations describe the fall of an apple and the collapse of a star. The same curvature that bends a photon's path also shapes the birth of galaxies. Time and space, energy and mass, all are expressions of a single fabric. The universe does not simply exist within this fabric, it is the fabric. But there is more to the story than equations and light. For gravity does not only bend the cosmos, it bends experience. What would it mean to live near such curvature? To witness the stretching of time not as theory but as sensation? To answer, we must turn our gaze to matter itself, to the way these forces act upon substance, the way they twist gas, dust, and plasma into radiant spirals. In the regions around black holes and neutron stars, gravity's artistry becomes visible as motion and flame. It is there, in the furious whirl of accretion disks, that the warping of space-time paints the universe in its most luminous colors. In the presence of extreme gravity, light itself forgets how to move in straight lines. Near the surface of a neutron star or the edge of a black hole, the curvature of space bends every photon into a curve of obedience. A ray of light that once set out to cross the void now spirals, trapped between geometry and destiny. From far away, what we see is not the object itself, but its distortion, the echo of light struggling to escape gravity's grip. To look at such a place is to see the universe through a lens made of time. The same moment can appear to stretch endlessly for one observer and flash in an instant for another. This is the consequence of curved space-time, where the passage of seconds and the path of light are both determined by gravity's will. The deeper the curve, the slower time becomes. The slower time becomes, the redder the light appears as its energy thins across distance. This redshift is not merely color, but memory, the record of time slowed by gravity. Imagine a spacecraft hovering near the event horizon of a black hole, held aloft by some impossible force. The crew would see the universe outside accelerate. Stars would drift faster, their orbits compressing into a blur of motion. If they watched the distant Earth, they would see it age rapidly, seasons flickering like heartbeat rhythms, years flowing in rivers of light. Meanwhile, their own time would seem unaltered. A clock aboard the ship would tick as always, but the universe beyond would rush toward its future. The same is true, though to a lesser degree, near a neutron star. Its gravity bends space-time enough that time slows significantly, but does not yet break. This slowing has been measured by observing pulsars, whose rotations act as cosmic metronomes. Their rhythm, when compared to the same type of star far away from strong gravity, reveals the stretching of time predicted by Einstein. Each pulse carries the trace of the star's weight upon space-time, a cosmic signature of delay. Gravitational lensing, the bending of light by massive bodies, is another expression of the same law. When a galaxy lies behind another, the foreground mass bends its light into arcs and rings, magnifying the hidden galaxy. Astronomers use these distortions to map dark matter, the unseen mass that fills the cosmos. The light curves tell us where gravity is strong, even when no visible object is present. The universe itself becomes a map drawn in warped light, a living testament to the way space is sculpted by mass. The deeper lesson is that space and time are not separate entities, but one fabric. A black hole is not a thing inside that fabric. It is a fold within it. A neutron star is not merely a sphere of matter, it is a ripple frozen into place. To speak of falling into a black hole is to speak of following the natural line of the fabric's curvature, the same way a ball rolls down a slope. But the slope here is time itself, bending inward toward eternity. At the event horizon, that bending reaches its limit. Light emitted sideways circles endlessly, forming the photon sphere. Light emitted upward loses its battle and turns back. Every direction leads inward, and time flows with it. To the outside world, this is the edge of visibility, but to the traveler, it is simply another step through space-time. The black hole is not an absence, but a continuation, a region where time replaces space, and the future points inward forever. Even Earth, gentle by comparison, is a small demonstration of this truth. Time at the surface flows more slowly than time in orbit. Astronauts aboard a satellite age slightly faster than those who remain on the ground. The difference is tiny, mere microseconds per day, yet it is enough that our global positioning systems must account for it. Without the corrections predicted by general relativity, every satellite signal would miss its mark by kilometers. Our navigation depends on our understanding of curved time. All of this shows that gravity is not an external force pressing upon the universe, but a property of its structure. Mass tells space how to curve, and curved space tells matter how to move. The stars do not circle the center of a galaxy because they are pulled. They circle because the geometry of the galaxy leaves them no other path. The planets orbit the sun not through attraction, but through obedience to the curvature of space-time around it. To understand this is to glimpse the unity of existence, the same geometry that governs the smallest ripple of a photon governs the path of entire galaxies. The universe is not a stage upon which matter moves. It is the movement itself, a living continuum of form and time. But what happens when this continuum is pushed beyond its limit? When matter and light no longer follow curved paths, but are torn apart by the gradients of gravity itself. Near the surfaces of neutron stars and the horizons of black holes, the difference in gravity between one side of an object and the other can exceed any force known to nature. It is there that curvature ceases to be gentle and becomes violent. It is there that gravity stops bending and begins to destroy. Around the mouths of black holes and the surfaces of neutron stars, matter is transformed into light. Gas, dust, and fragments of shattered stars do not fall directly into darkness. They circle first, spiraling inward through a storm of friction and heat. This whirl of matter is called an accretion disk, and it is among the most violent and luminous structures in the universe. From a distance, the disk seems thin, delicate, almost serene, but up close, it is a furnace beyond imagination. The particles within it move at nearly the speed of light, colliding and shearing against one another. Each collision releases energy, and that energy heats the gas until it glows in X-rays and gamma rays. The temperature can reach tens of millions of degrees Celsius, hot enough to strip atoms of every electron, turning matter into pure plasma. This is not fire in any ordinary sense, it is light born from motion and gravity. The spiral shape of the disk is inevitable. Gravity draws matter inward, but angular momentum resists collapse. Each particle wants to fall, yet its spin keeps it circling. The balance between these two motions, falling and orbiting, creates the disk. As particles rub together, friction steals energy from their motion, allowing them to move closer to the center. The lost energy escapes as radiation. The process repeats endlessly, and the inward journey becomes a slow surrender, each orbit tighter and faster than the last. Near a neutron star, the disk meets a surface. The infalling matter slams into a crust of nuclear density, releasing enormous bursts of energy. These impacts can trigger flashes of X-rays so bright they outshine entire galaxies for brief moments. The neutron star becomes a beacon, pulsing with heat and light. Because it has a solid surface, it radiates directly, turning gravitational energy into radiation with brutal efficiency. A black hole, by contrast, has no surface. Matter falling into its disk spirals closer and closer until it crosses the event horizon and vanishes. The energy it releases before that moment is all that can be seen. Once inside, there is no return, no radiation, no echo. The black hole swallows not only matter, but information itself. The difference between a neutron star and a black hole is therefore not only in density or size, but in the fate of light. The neutron star gives its energy back to the universe. The black hole takes it away. The region closest to the black hole, just outside the event horizon, is known as the innermost stable circular orbit. Beyond this boundary, no orbit can last. A particle that crosses it must fall inward inevitably. This orbit defines the edge of the visible disk, the final ring of light, before descent into the unknown. The brightness of this ring tells us the mass and spin of the black hole. The faster the black hole rotates, the closer this orbit lies to the horizon, and the more energy the disk can release. When matter spirals inward, it carries magnetic fields with it. These fields twist and tangle under the enormous pressures, channeling energy into streams that shoot away from the poles. These are relativistic jets, narrow beams of plasma that travel for thousands of light years, carrying part of the black hole's rotation energy into intergalactic space. The process is still not completely understood, but it shows that even as black holes consume, they also give back, shaping galaxies through their outflows. Around neutron stars, similar jets can form, though their origins differ. The star's magnetic field, often trillions of times stronger than Earth's, guides plasma into beams that pulse with rotation. When aligned with our line of sight, these appear as pulsars, their light sweeping across the sky in perfect intervals. The difference between a neutron star and a black hole is visible here too. The pulsar's light comes from its surface and magnetism, while the black hole's jets come from the energy of space-time itself. The radiation from these disks reveals the extreme physics at play. X-ray telescopes record bursts, flares, and steady glows from binary systems where one ordinary star feeds matter to its collapsed companion. The flow of gas from the living star forms a bridge across space, falling into the waiting gravity well. This process, called accretion, converts a fraction of mass into light, far more efficiently than fusion. In fusion, less than 1% of mass becomes energy. In accretion, up to 40% may be released before matter vanishes. Gravity, not chemistry or nuclear reaction, becomes the ultimate engine. Every photon escaping from these disks tells a story written in motion. The spectrum of light, from radio to gamma rays, encodes the speed, density, and temperature of the plasma. By studying the flicker and rhythm of that radiation, astronomers reconstruct the invisible architecture of these systems. They measure spin rates, magnetic fields, and even the bending of space-time near the horizon. In this way, light itself becomes a probe of gravity. What is most astonishing is that this process of destruction also sustains creation. The energy released by accretion heats interstellar gas, drives winds that trigger star formation, and influences the growth of galaxies. The same forces that tear matter apart also build new worlds. The black hole and neutron star, each consuming their surroundings, serve as engines of cosmic balance. To the human eye, the sight of such a disk would be hypnotic, a glowing ring of fire surrounding a hole of perfect darkness. Its inner edge would pulse with colors beyond ordinary vision, its outer rim fading into the void. The contrast between the radiant fury of the disk and the stillness of the shadow is perhaps the universe's most dramatic image. Creation and annihilation, bound together in one eternal motion. In these places, gravity's artistry reaches its most visible form. The shapes we see, the arcs, rings, and spirals, are not objects, but paths. They are the handwriting of space-time itself, illuminated by matter in its final act. Each photon is a farewell note, escaping just before being lost forever. The light we see today from accretion disks around distant black holes began its journey millions or billions of years ago, crossing the universe to show us what happens when gravity takes command. But even the brilliance of an accretion disk cannot tell the whole story. For in these regions of furious energy, another mystery hides: how gravity turns motion into power, how rotation itself can feed light, and how the darkest objects can become the brightest beacons. To understand that, we must look beyond the visible and study the conversion of gravity into energy itself. There, in the interaction between field and motion, the universe reveals how even darkness can shine. To follow the spiral deeper is to enter the true furnace of gravity. Within the accretion disk, everything is in motion, and motion itself becomes heat. Friction between streams of plasma is no gentle brushing of particles, but a collision of energies. Electrons and ions tear past each other, creating magnetic turbulence that twists like living currents. The field lines snap and reconnect, releasing bursts of radiation that light the void. Each flash is the product of pure conversion, mass, and motion, turning into light without the need for fusion, chemistry, or fire. The airless space near the black hole is filled with invisible storms. Magnetic fields rise and fall like waves, accelerating matter to near light speed. Protons spiral along these lines, emitting synchrotron radiation that flickers through the electromagnetic spectrum. The disk becomes a luminous veil surrounding perfect darkness, a halo of destruction so hot that atoms themselves can no longer exist. Hydrogen and helium, once the gentle fuel of stars, are stripped into their subatomic forms. The universe's simplest elements become raw energy. If one could see this directly, the sight would challenge understanding. The inner regions of the disk would shine with blinding brilliance, a ring of energy circling the black hole's shadow. Around it, light would bend backward, creating echoes of itself. multiple images of the same arc, spiraling inward. The closer to the horizon, the slower the motion would appear, until time and light seem to merge. From far away, the image is not chaos but symmetry, a perfect balance of brightness and darkness, order sculpted from collapse. In the case of a neutron star, the story changes at the last instant. The disk does not end in disappearance, but in impact. Matter striking the star's surface releases its energy in sudden bursts, producing flashes of X-rays that sweep through space. These bursts can repeat with astonishing regularity, each one marking the rotation of the star beneath. Some neutron stars become X-ray pulsars, their steady rhythm a beacon of gravity's endurance. Others produce irregular flares, the signatures of unstable flows, and sudden magnetic reconnections on their surfaces. The difference between these two fates, one with a surface, one without, defines the boundary between matter and geometry. The neutron star is still a place. The black hole is not. On a neutron star, infalling gas ends its journey with a collision, releasing light that can escape. Around a black hole, the gas releases its energy on the way down, but its final moment vanishes beyond the horizon. The light we see is a farewell, the last visible act of matter, before it ceases to exist as anything other than curvature. This difference gives each its own kind of brilliance. A neutron star's radiation is pulsed, patterned, tied to the rotation of a physical surface. A black hole's disk glows continuously, shaped by the fluid motions of plasma and the deep potential of space-time. In both, gravity acts as a sculptor, converting fall into flame. But while the neutron star's light comes from matter's defiance, the black hole's comes from surrender. The energy released in these disks is staggering. A single gram of matter falling toward a black hole can produce more energy than the burning of thousands of tons of coal. A stream of gas flowing from a companion star can power a quasar so bright it outshines an entire galaxy. In these systems, gravity becomes the most efficient engine in the cosmos. The conversion of potential energy into radiation approaches the theoretical limit set by physics itself. Even the most advanced civilization could not design a machine more perfect in its efficiency. Some of the radiation escapes as jets, colossal beams of plasma launched perpendicular to the disk. These jets move at nearly the speed of light, cutting through interstellar space for thousands of light years. Their formation is still one of the deepest mysteries in astrophysics. The leading theories suggest that the black hole's rotation twists magnetic fields into tight spirals, flinging charged particles outward through the ergosphere. The process converts rotational energy into motion, allowing the black hole to lose spin over time. Through these jets, energy stolen from gravity is returned to the universe. Supermassive black holes at the centers of galaxies produce the most magnificent of these phenomena. When their accretion disks are active, they form quasars, objects so bright they can be seen across billions of light years. The light from some quasars began its journey when the universe was young, long before the formation of the sunday. To look at one is to see time itself illuminated by gravity. The power released is beyond comprehension, yet it follows simple rules. Every photon, every jet, every burst is the inevitable consequence of matter obeying the curvature of space-time. Even in their violence, accretion disks are ordered. Their turbulence, though chaotic in motion, maintains balance on cosmic scales. The inward flow of matter is matched by the outward flow of energy. The temperature gradient, the density profile, the magnetic field, all follow laws that can be written in equations. The result is beauty born of balance, a system that destroys and creates simultaneously, maintaining harmony between loss and illumination. This harmony connects back to everything gravity touches. The energy that escapes from accretion disks heats interstellar gas, triggers the birth of new stars, and helps regulate the growth of galaxies. Black holes, once thought to be cosmic endpoints, are in truth engines of cosmic evolution. They recycle matter and energy, turning collapse into creation. The brightest galaxies owe their light to the darkest hearts. To grasp this is to understand that gravity does not only pull, it transforms. It turns motion into light, structure into flow, and death into radiance. The accretion disk is gravity's masterpiece in motion, the visible proof that even near total destruction, the universe remains balanced, elegant, and exact. But the furnace is not endless. Matter that falls inward feeds the light for only so long before the reservoir runs dry. When the disk thins, the glow fades, and the black hole returns to darkness. What remains then is the memory of energy, a lingering heat in the fabric of space. It is here that we begin to see the true power of gravity, not only to shape matter, but to release the deepest energy hidden within it. From these glowing rings of fire, we step into the next question. How does gravity turn so much darkness into light? What unseen mechanisms channel the fury of motion into the harmony of radiation? To understand this, we must follow the energy itself, tracing how it emerges, how it escapes, and how it powers the cosmos from the edge of oblivion. Within the accretion disk, gravity and energy engage in a dialogue older than stars. Every orbit, every collision, every photon released is part of a conversation written in the mathematics of space-time. The deeper the fall, the greater the heat, until motion itself becomes light. The matter spiraling inward does not resist. It obeys, surrendering mass for illumination. It is through this surrender that the universe glows. At the inner edge of the disk, close to the event horizon or the neutron star's surface, the energy reaches its peak. Here, matter moves so fast that a fraction of its rest mass is converted into radiation. For a black hole, this process can release up to 40% of the infalling material's mass as energy far beyond the efficiency of nuclear fusion, which yields less than 1%. Gravity, relentless and absolute, proves to be the most powerful generator in the cosmos. Around a neutron star, the scene is even more dynamic. The surface, though impossibly dense, interacts with the swirling plasma. As gas crashes down, it forms hotspots that flash and fade in rhythm with the star's rotation. These flashes create X-ray pulsations so precise that astronomers can measure changes in the star's spin to within millionths of a second. Each pulse marks the point where matter meets the final barrier, the crust of neutrons packed tighter than atomic nuclei. The resulting light is not just brightness. It is the final signature of matter completing its transformation into energy. The black hole, by contrast, holds no such meeting. There is no impact, no surface to strike, no final burst. All that remains is the approach. The disk's inner edge glows, then dims, and the particles disappear silently. What happens beyond the event horizon is unknowable, but the light emitted just before the fall carries all the evidence needed. By studying this radiation, scientists can measure the spin of the black hole, its mass, and even the geometry of the surrounding space-time. The patterns of light reveal the curvature itself. These disks also speak in sound, though not sound in the way human ears can perceive. Their oscillations, fluctuations in brightness, density, and magnetic tension produce vibrations that ripple through space-time. Detectors record these as quasi-periodic oscillations, faint echoes of motion near the edge of the possible. Each fluctuation tells of turbulence, of friction, of gravity sculpting energy from chaos. It is as if the universe hums softly at the edge of a black hole, the vibration of creation itself. The radiation from accretion disks travels across unimaginable distances, carrying information through the cosmic dark. Some of it reaches Earth after millions or even billions of years. In that light are encoded the fingerprints of gravity, redshifted lines, broadened spectra, and subtle variations that tell of immense motion. When astronomers decode these patterns, they read the story of matter's last moments before being transformed. Every X-ray burst and every spectral line is a message from the frontier of physics. In some systems, these messages come in sudden flashes known as bursts. A neutron star gathering matter from a companion can build a thin layer of gas on its surface. When the layer becomes dense enough, nuclear fusion ignites in a runaway reaction, releasing a burst of energy that sweeps across space. These thermonuclear bursts last only seconds, but radiate with the power of millions of suns. They are the heartbeat of an engine that never truly rests. Even more mysterious are the transient events where black holes suddenly awaken. When a wandering cloud of gas or the remnants of a shattered star drift too close, the dormant black hole feeds again. The disk brightens, the jets flare, and the system becomes visible across the galaxy. Then, as the fuel runs out, it fades back into silence. These cycles of feeding and quiet define the life of an accreting black hole, a pulse measured not in seconds, but in centuries. At the grandest scales, the same process powers quasars, the blazing hearts of ancient galaxies. In the early universe, black holes fed greedily, consuming gas at incredible rates. Their disks burned with light that has crossed billions of years to reach us. Some of these quasars shine brighter than entire galaxies combined, their luminosity dwarfing the energy output of trillions of stars. Yet at their core, the mechanism is the same as in a small binary system: gravity converting motion into radiation. This unity across scales from stellar remnants to galactic centers shows that gravity is not chaotic, but consistent. It behaves the same way everywhere, following laws that never falter. Whether the mass is a few times that of the sun or billions, the same balance of forces governs the disk. The same curvature shapes the light. The same geometry dictates the energy. The difference is only in magnitude, not in nature. When we observe these disks, we witness the universe's most direct expression of transformation. Matter, the substance of creation, becomes light, the messenger of existence. What falls inward does not vanish entirely. Part of it is returned as illumination, as warmth, as radiation that travels outward forever. Even as black holes consume, they cannot help but shine. This paradox, darkness creating light, is not a contradiction, but the essence of gravity's perfection. Eventually, as the supply of matter diminishes, the disk fades. The remaining plasma cools and drifts into the black hole or the neutron star. The light weakens, the jets wane, and the system grows quiet once more. Yet its influence remains. The surrounding space carries the mark of the outflows, the heat of the radiation, and the shockwaves that trigger new stars to form. Nothing is wasted. Every act of destruction becomes a seed for creation elsewhere. In this way, accretion is not a process of consumption, but of renewal. The light born from these disks nourishes the cosmos, shaping galaxies, warming interstellar clouds, and driving the cycle of birth and death that defines the universe. The furnace of gravity, though terrible, is also generous. It gives back what it takes, transmuting matter into energy, and energy into the architecture of the cosmos. From here, the path leads naturally to the next question: how this light, born from gravity, carries the story of energy itself. For both black holes and neutron stars are not only destroyers but engines, turning rotation, magnetism, and mass into power. To understand them fully, we must step into the next domain, where light, energy, and motion become indistinguishable, and the cosmos reveals its most efficient designs. Energy is the language of the universe, and gravity is its most fluent speaker. In the presence of extreme mass, the boundary between matter and radiation blurs. What was once a solid star becomes a machine for light, and what was once motion becomes power. Around neutron stars and black holes, this transformation is absolute. Gravity and rotation weave together to forge the brightest, most efficient engines in existence. A neutron star, though small, spins with terrifying speed. Some rotate hundreds of times each second, their surfaces moving at a fraction of the speed of light. This rotation, combined with their immense magnetic fields, turns them into cosmic generators. Charged particles trapped in those fields are whipped into spirals, accelerated to energies far beyond anything achievable on Earth. As they move, They emit beams of radiation that sweep through space like the beams of a lighthouse. When those beams cross Earth, we detect them as pulses, regular and precise. Each pulse is the signature of a star that has turned its death into rhythm. The light from a pulsar carries with it the geometry of the star's magnetism. The field lines emerge from the poles, twisting into loops that stretch thousands of kilometers outward. Electrons race along them, emitting radio waves, X-rays, and sometimes gamma rays. The process is so exact that pulsars can serve as cosmic clocks. Their timing drifts by less than a millionth of a second per year. Through them, astronomers have tested Einstein's equations, measured the distortion of space-time, and even detected the faint murmurs of gravitational waves passing through the galaxy. In these engines, gravity is only one part of the equation. Magnetism, born from the motion of charged particles within the star, amplifies the energy. The field is so strong that it can pull atoms apart, stretching electrons from nuclei. The space around the star becomes a soup of charged particles, a plasma that dances to the magnetic rhythm. Some neutron stars are even more extreme. These are magnetars, with fields 1,000 times stronger than ordinary pulsars. When their magnetic crusts shift, they release bursts of gamma rays, so intense they can momentarily outshine the rest of the galaxy. Black holes, too, are engines, though, of a different kind. They have no surface, no crust, no magnetic core. Their power comes from rotation itself. A spinning black hole drags space-time around it, twisting the nearby magnetic fields into coiled springs. The rotational energy can be extracted through this interaction, channeling it into the jets that stream from the poles. This process, described by physicists as the Penrose mechanism and later refined into the Blandford-Znajek model, allows energy to escape from what seems like a perfect trap. The black hole loses a fraction of its spin, while releasing power measured in trillions of suns. To visualize this, imagine the region just outside the event horizon, the ergosphere. Within it, space-time is dragged along so strongly that nothing can remain still. Every object, even light, must rotate with the black hole. It is here that particles can gain energy by splitting one part falling inward, the other escaping outward with more speed than it had before. This exchange turns rotation into radiation, drawing power from the spin of space-time itself. The energy released by these processes fuels the universe's most radiant phenomena. Quasars, blazars, and active galactic nuclei all owe their brightness to black holes feeding through accretion and spin. Their light travels across billions of light years, reaching us as faint whispers from the dawn of time. Each photon is a messenger of gravity turned radiant, the residue of motion too fast and fields too strong to imagine. Around neutron stars, energy finds other paths to escape. Their magnetic poles accelerate particles outward in twin beams that sweep through space. The mechanism is intricate. As the magnetic field rotates, it induces electric fields that hurl electrons and positrons to relativistic speeds. The particles then emit radiation through synchrotron and curvature processes, light born from the turning of charges through warped space. These emissions span the spectrum, from radio waves to gamma rays, and they tell us how energy moves through matter when gravity's grip is nearly absolute. Even when quiet, neutron stars radiate steadily. Their surfaces glow with residual heat, cooled slowly over millions of years. Some are surrounded by clouds of plasma called pulsar wind nebulae, formed by the steady outflow of particles driven by the star's rotation. These nebulae shimmer in X-rays and visible light, vast bubbles of energy, inflated by the power of a single collapsed core. The Crab Nebula, the remnant of a supernova seen on Earth nearly 1,000 years ago, is one of the finest examples, a cloud of light powered by a neutron star only a few kilometers wide. The efficiency of these objects defies intuition. A single teaspoon of neutron star material weighs billions of tons, and the energy it can release through gravity or magnetism surpasses any known source. Black holes take this efficiency to its theoretical limit. The energy extracted from their disks and spins surpasses what any process of nuclear burning could achieve. They are not engines of destruction, but of conversion perfect machines where matter, motion, and space-time cooperate to produce brilliance. The light they emit tells us not only about their power, but about their structure. Polarization measurements reveal the orientation of magnetic fields. Spectral shifts reveal velocities near the speed of light. Periodic flickers betray the presence of companions or orbiting clumps within the disks. Each observation allows physicists to map the invisible architecture of gravity itself. The behavior of light becomes a blueprint of space-time. And even as we observe, these systems evolve. A black hole that feeds too much slows its spin as energy escapes through jets. A pulsar gradually loses its rotation as it radiates, its period lengthening, its beams weakening. Yet even in decline, they remain active for millions of years, their influence spreading across light years of space. The energy they release stirs interstellar gas, seeds new stars, and forges the heavy elements that make planets and life possible. In this way, what begins as collapse becomes creation again. The universe wastes nothing. Gravity takes the end of a star and turns it into a lamp that illuminates galaxies. It is the most relentless recycler imaginable, transforming loss into power, silence into radiance. And though these engines differ, one bounded by a surface, the other by a horizon, they share the same origin. Both are born from the balance between pressure and collapse, from the breaking of equilibrium. The neutron star resists, the black hole yields, but both become sources of light through the same geometry. Their existence shows that energy and gravity are not opposites, but partners. One curves space, the other escapes through that curvature, together shaping the flow of the cosmos. Yet for all their power, both possess regions where their dominion becomes lethal. Beyond the generation of light lies the destruction of form. The same forces that create energy can also tear apart any object that ventures too near. To explore that boundary is to witness gravity's violence, to see what happens when the pull of space-time becomes stronger than the strength of matter itself. It is there, near the edge of survival, that the next chapter begins, the spaghettification zone, where even atoms cannot remain whole. There are regions in the universe where gravity does not simply attract, it disassembles. Here, the pull is not uniform, but uneven, so extreme that the difference between one end of an object and the other becomes fatal. This is tidal gravity at its most merciless, where the gradient of space-time curvature stretches, crushes, and tears apart anything that dares to fall too close. Astronomers call this process spaghettification, a word almost playful for a phenomenon that marks the limit of survival itself. Imagine approaching a neutron star. Its surface gravity is already 200 billion times stronger than Earth's. A human body, even a solid rock, would never reach that surface intact. The difference in pull between your head and your feet would exceed every binding force that holds matter together. Molecules would stretch, atoms would distort, and electrons would be stripped from nuclei long before impact. Matter would flatten into a layer of subatomic particles before being absorbed into the crust of neutrons below. On a neutron star, gravity is so fierce that the word surface barely applies. It is not ground, but a boundary of condensed nuclear matter, a solid lattice of neutrons, packed tighter than any material in existence. Yet even this devastation pales beside what awaits near a black hole. A neutron star still has a surface to stop the fall, but a black hole does not. As one draws closer, the difference in gravitational pull between near and far sides grows exponentially. This differential, this stretching force, becomes stronger than any material can endure. It is not a crushing blow, but a progressive unmaking. The body elongates, its parts accelerating at different rates, the gradient widening until structure itself cannot survive. If you were to fall feet first toward a small black hole, perhaps a few times the mass of the sun, your legs would be pulled far harder than your head. In microseconds, you would be drawn out like a thread, thinner and longer, until the very atoms that once composed you were torn apart by tidal acceleration. These atoms would then be stripped into subatomic particles, forming a stream of plasma spiraling inward, each fragment following its own curved path toward the event horizon. The scale of this destruction depends on the mass of the black hole. Paradoxically, the smaller the black hole, the more lethal its tidal forces near the horizon. A supermassive black hole, millions or billions of solar masses, has an event horizon so vast that the gradient across a human body or even across a planet would be mild at first. One could, in theory, cross its horizon without noticing an immediate difference. Only deep within, near the singularity itself, would the spaghettification become absolute. Time and space would stretch into incomprehensible forms, and all separation between length and duration would collapse into unity. For smaller stellar black holes, the transition is abrupt and violent. The tidal field grows so quickly that even before reaching the horizon, an infalling object is torn apart. The event horizon becomes not a boundary, but a grave. The light emitted from the disintegration, distorted by the curvature of space-time, would flicker and fade as it climbs out of the gravitational well. To a distant observer, this light would seem to slow and redden, a final luminous signature of destruction before darkness swallows it whole. The physics behind spaghettification lies in the geometry of curvature. Gravity is not a pull downward, but a warping of space-time inward. Near a massive body, the lines of this curvature diverge sharply. The closer an object is, the steeper the curve. Thus, one side of a body experiences a different path through space-time than the other. The difference in these paths in their acceleration through curved geometry creates the stretching. Where the curvature changes rapidly, the tidal forces become enormous. In the language of Einstein's equations, these differences are encoded in the Riemann curvature tensor, the mathematical object that measures how much space-time bends from point to point. Where that tensor grows large, reality itself becomes uneven. The same geometry that guides planets around stars becomes, at these extremes, a mechanism of annihilation. Near a neutron star, this tidal force is steep but finite. A spacecraft, if strong enough, could orbit at a safe distance without disintegration. The line between survival and destruction lies only a few kilometers above the surface. For black holes, the boundary is far more complex. The closer one moves, the faster the divergence grows, until the concept of distance loses meaning. Inside the event horizon, every direction points inward, and time itself becomes the coordinate of collapse. The spaghettification is no longer a force acting on matter. It is the inevitable progression of time. No known material can resist these gradients. Even the atomic nucleus, bound by the strongest force in nature, would eventually yield. Quarks and gluons, the fundamental constituents of protons and neutrons, might be stretched into exotic states of matter, perhaps forming quark-gluon plasmas, or other, yet unknown configurations. Some theories suggest that near the singularity, matter and energy become indistinguishable, the curvature so intense that all definitions of form vanish. From a distance, these tidal events are visible only through light and energy. When a star ventures too close to a black hole, it is torn apart in a tidal disruption event. The star's outer layers are pulled into long streams that wrap around the black hole, colliding and heating until they flare with the brightness of a supernova. These cosmic feasts reveal the presence of otherwise invisible black holes. Each flash, each outburst, is the death cry of a star transformed into radiation. These same forces play out on smaller scales as well. In binary systems where a neutron star or black hole feeds on a companion, the victim star is gradually stripped by gravity. Gas flows from its outer layers toward the denser object, forming an accretion stream. This steady spaghettification fuels the disk, sustaining its radiance. The slow tearing apart of one star becomes the heartbeat of another's hunger. In this dance of creation and destruction, there is a strange symmetry. The same curvature that stretches and tears also gives rise to beauty, the arcs of light bent by gravitational lensing, the rings and jets of glowing plasma, the elegant equations that predict their behavior. Gravity is not cruel by choice. It is geometry made manifest, indifferent, yet perfect. The ultimate fate of anything that crosses a black hole's horizon is unknowable. From outside, all signals cease. From inside, time and space switch roles. The stretching that began as a force becomes the flow of time itself, leading inevitably toward the singularity. Whether matter truly ends there, or whether new physics intervenes, remains one of the deepest questions in science. Some theories suggest that quantum effects may smooth out the singularity, turning it into a bridge or bounce. Others hold that information may never truly be lost, but encoded in the horizon's surface. Whatever the truth, one thing is certain. In the spaghettification zone, the familiar rules of existence collapse. The universe, usually so continuous and comprehensible, reveals its most alien aspect. It is here, at the intersection of gravity and quantum law, that the cosmos hides its final secrets. And yet, these same forces, destructive as they seem, have shaped everything we see. The death of stars, seeds, galaxies with elements. The merging of black holes sends ripples through space-time, and the stretching of matter into light fuels the cosmic cycle. From the smallest atom to the largest cluster of galaxies, gravity's reach is both creative and consuming. In the next step of our journey, we rise from the edge of death to the scale of creation. For the same black holes and neutron stars that destroy also build forging elements, shaping galaxies, and writing the structure of the cosmos itself. In their shadows, the universe becomes an architect. From the ashes of collapse, the universe begins to build. Every act of destruction in the cosmos feeds a new creation. Every implosion seeds new life. Neutron stars and black holes, born from death, become the architects of galaxies. Their gravity sculpts the interstellar medium. Their radiation heats the void, and their collisions forge the elements from which worlds and beings are made. In their silent power, they are the sculptors of time and matter. When two neutron stars orbit one another, their dance is long and slow. They spiral closer through the emission of gravitational waves, ripples in space-time itself. Each orbit drains a little energy, shrinking the distance between them. The closer they come, the faster they move, until in their final seconds they circle each other hundreds of times per second. Then, with a shudder felt across the universe, they merge. For billions of years, these collisions were only theory, but in the year 2017, the detectors of LIGO and Virgo captured the first faint tremor of space-time from such an event, followed moments later by a flash of light. It was the first time humanity saw and heard the universe in concert, gravity and light telling the same story. The merging neutron stars released more energy in a few seconds than all the stars in the visible universe combined, not as radiation, but as the distortion of space-time itself. From that collision came something extraordinary. The debris, compressed to densities beyond imagination, created conditions where protons and neutrons fused into heavier elements: gold, platinum, uranium, and all the rare metals of the cosmos. Each atom of gold in every ring, each speck of platinum in every circuit, was once part of a star destroyed in a cosmic collision. When those elements scattered through the galaxy, they mixed into the gas clouds that would later form new stars and planets. Every breath of air, every handful of soil, carries the memory of a neutron star's death. This process, known as R-process nucleosynthesis, requires conditions of immense neutron density and rapid cooling. Ordinary stars cannot achieve it, but merging neutron stars and some kinds of supernovae can. In those brief instants, matter is bombarded by neutrons faster than it can decay, building the heaviest nuclei nature allows. These newly forged elements then disperse in shock waves that enrich interstellar space. From that enriched dust come planets, oceans, and eventually, observers who can look back and recognize their origin. Black holes also shape the cosmos, though their work is more subtle and vast. At the centers of galaxies lie supermassive black holes, millions to billions of times the mass of the Sunday. They anchor the structure of the galaxies themselves, their gravity defining the orbits of billions of stars. When active, these giants consume gas and dust, producing energy that outshines the entire galaxy. The radiation from their accretion disks and jets regulates star formation, heating surrounding gas and preventing it from collapsing too quickly. This feedback controls the pace of galactic evolution. Without it, galaxies would form stars too rapidly, exhausting their gas and fading young. With it, they maintain balance, a slow cycle of birth and renewal that lasts billions of years. In this way, black holes act not as destroyers, but as regulators, cosmic governors of creation. The evidence of this influence is everywhere. Galaxies with larger central black holes tend to be more massive, their bulges more luminous. The mass of the black hole is directly correlated with the properties of its host, a relationship known as the M-sigma relation. It suggests that galaxies and their central black holes grow together, each shaping the other through feedback and gravity. The universe is not random in its architecture. It is coevolution, written in light and darkness. Beyond structure, black holes also shape time. When they merge, their gravitational waves ripple outward, carrying information about their mass and spin. These waves stretch and squeeze space-time itself, traveling across billions of light-years without losing form. Instruments on Earth can detect these ripples as changes smaller than a proton's width, translating the language of gravity into sound. Each detection is a message from the distant past, the record of a cosmic event long gone, yet still resonating through the universe. Some black hole mergers create new black holes, heavier and faster spinning than their parents. The excess energy escapes as gravitational radiation, a sigh from the geometry of space-time as it settles into a new shape. Others may produce electromagnetic flashes, revealing their environment, the surrounding gas, dust, or even stars caught in the collision's wake. These events remind us that the universe is not static but alive, its fabric constantly reshaped by motion and mass. Neutron stars too leave long legacies. As pulsars, they emit beams that can sculpt their surroundings. Their winds of charged particles carve out cavities in interstellar clouds, forming bubbles of light and energy. Over millions of years, these bubbles expand, mix, and merge, driving the chemistry that leads to complex molecules. The same magnetic storms that tear matter apart near a neutron star also create the building blocks of life in far-off regions of space. When we look at the Milky Way, we see not a static disk of stars, but a living organism. Its spiral arms are shaped by gravity waves, its gas clouds stirred by the echoes of supernovae and mergers. Every bright nebula, every star nursery, owes part of its existence to the energy released by collapse. The death of massive stars enriches the galaxy. The collisions of remnants reorder it, and the black holes at its heart regulate its future. In this grand cycle, gravity serves as both destroyer and designer. It builds complexity from simplicity, order from chaos. A collapsing core becomes a neutron star. The merger of neutron stars creates elements. Those elements form planets, and planets, in time, give rise to awareness. The cosmos uses death to create mind. Even at the largest scales, the fingerprints of this process remain. Clusters of galaxies emit X-rays from gas heated by gravitational infall. Dark matter, invisible but massive, bends light and guides formation. Everywhere, the same principle repeats. Energy, released through collapse, becomes the blueprint for structure. When we trace this pattern backward, we arrive at the beginning, the first stars, the first black holes, the first galaxies. Their formation set the stage for everything that followed. The same physics that governs a neutron star's crust or a black hole's spin shaped the early universe. The architects of modern galaxies were the same forces that sculpted space-time itself. Yet even this grand architecture has boundaries. The universe, vast and ancient, is not infinite in its detail. It evolves, expands, cools, and changes. The black holes that once illuminated galaxies will one day fade as fuel runs out. The neutron stars will cool into silent spheres of degenerate matter, but the elements they created will endure, scattered across the stars that remain. The architecture will persist, even after the architects have gone. In their dual nature, creative and destructive neutron stars and black holes reflect the universe's fundamental truth. Energy and entropy, order and decay, are inseparable. One gives meaning to the other. The cosmos itself is a balance between collapse and expansion, between the inward pull of gravity and the outward push of light. From this balance arises beauty. Every galaxy, every atom, every mind is a product of that equilibrium. The universe does not design deliberately, but through necessity, and from that necessity comes harmony. The architects, black holes, and neutron stars are simply the most visible expressions of that harmony, working silently, endlessly, with the patience of eternity. And yet, for all their grandeur, they are not opposites. They are siblings, born from the same process, divided only by degree. One compresses matter into its final form. The other carries compression to its ultimate consequence. One radiates light from its surface. The other hides light within its horizon. Together they form the two faces of gravity, finite and infinite, luminous and dark, creation and oblivion, intertwined. In their presence, the universe reveals both its fragility and its endurance. From the smallest ripple of a gravitational wave to the sweep of a galactic arm, everything flows from the same law. Mass curves space-time, and curved space-time shapes destiny. The architects of the cosmos do not build with hands or plans, but with the inevitability of geometry itself. From this understanding, one final question arises. If these forces can shape galaxies and forge elements, what is the ultimate expression of their power? Between the neutron star's defiance and the black hole's surrender lies the purest contest of gravity's nature. To witness it is to stand before the final mirror of the cosmos, where all motion, energy, and curvature converge. The story of gravity begins with the stars, and it ends where light itself falters. Every collapse, every flash, every spiral of creation leads here to the confrontation between two of nature's final forms. The neutron star, dense beyond imagination but still finite, stands at the brink of matter's endurance. The black hole, infinite in simplicity, represents gravity unbound. Between them lies the narrowest of thresholds, the line between something and nothing, between surface and horizon. To compare them is to weigh the universe's most extreme possibilities. Both are born from the deaths of massive stars, yet they embody opposite destinies. A neutron star resists gravity through the pressure of neutrons packed together, each one refusing to collapse further. A black hole surrenders completely, its matter crossing a point from which not even light can escape. One preserves form, the other erases it. But both are ruled by the same law that gravity is not a force in the ordinary sense, but the shape of space and the rhythm of time. Imagine standing near a neutron star's surface. The ground beneath your feet is a lattice of nuclear matter, atoms crushed until the spaces within their nuclei have vanished. A single teaspoon of that material would weigh billions of tons. The curvature of space-time there is immense, bending even light into tight arcs. Clocks slow drastically, seconds stretching as gravity deepens. If you dropped an object, it would fall at nearly half the speed of light, before striking the surface in an explosion of pure energy. Yet, for all this violence, the neutron star remains a thing, a solid, measurable sphere, with boundaries, with a magnetic field, with rhythm. Now imagine descending toward a black hole. There is no surface to land upon, no solid resistance waiting below. The event horizon is not a place in the ordinary sense. It is a boundary in time, a point beyond which all paths curve inward. From far away, the black hole's gravity appears infinite, but this is a misunderstanding. At any distance outside the horizon, the pull can be measured and finite. It is only the slope of space-time that becomes absolute, the gradient that allows no return. Inside, the rules of space and time, reverse motion, becomes destiny, and the future points inward. If both objects were placed side by side, their differences would be subtle at first glance. Each would warp the surrounding light, bending space into strange halos. Yet the neutron star's glow would pulse and flicker, while the black hole's light would come only from the matter orbiting it. The neutron star would radiate directly from its surface, while the black hole would be framed by an accretion disk, a whirl of plasma, heated by the fall of matter into darkness. Both would appear surrounded by arcs of light distorted by gravity's lensing, but in the black hole's case, the center would remain utterly black, the shadow of the horizon. Their energies, too, tell the tale of contrast. The neutron star shines through motion and magnetism, its rotational energy radiating outward as pulses of radio and X-rays. The black hole shines through theft by converting the gravitational energy of falling matter into heat and light. Yet paradoxically, the black hole can be the more efficient source. The conversion of mass into radiation through accretion near a spinning black hole can exceed 40% efficiency, surpassing every other process known to physics. The black hole, though it swallows, gives back more energy than the neutron star ever could. Even the experience of time diverges between the two. Near a neutron star, time slows but continues. Near a black hole, time stops at the horizon for all observers watching from afar. An astronaut falling into a neutron star would be crushed instantly, yet their destruction would be visible. One falling into a black hole would disappear gradually, their image redshifting and fading, frozen on the edge of the event horizon forever. From their own point of view, the fall would be swift, the horizon crossed in seconds, but to the outside universe, the moment would never arrive. The difference is not just physical, but existential. One object allows the universe to witness its violence, the other hides it in silence. Both possess enormous gravitational power, yet the way they wield it is different. A neutron star's pull, while extreme, can be countered by speed or orbital motion. A spacecraft could, in theory, orbit it just above the surface, skimming the edge of its deadly field. A black hole, however, leaves no such refuge once the critical radius is crossed. The innermost stable orbit marks the final circle before descent, and beyond that, no trajectory endures. Gravity becomes not an attraction, but a command. Despite their differences, the two are connected by a fine line in physics. The Tolman, Oppenheimer, Volkoff limit, the maximum mass a neutron star can sustain before collapsing into a black hole. For most equations, this limit lies near 2 or 3 times the mass of the Sunday. Add a fraction more, and the pressure that holds neutrons apart can no longer resist gravity's inward curve. The star's surface disappears, replaced by an event horizon. In an instant, the geometry changes from resistance to surrender. The neutron star does not explode, it simply falls through its own shadow. At this threshold, matter and space-time exchange roles. What was once substance becomes curvature, and what was once pressure becomes destiny. The transition is invisible, no flash, no explosion, only a subtle shift in the mathematics of being. The universe does not mark the moment with spectacle, but with silence. One object ceases to exist as matter and continues as geometry. In their essence, these two remnants show us the full spectrum of gravity's power. The neutron star, is gravity constrained, immense, but held in check by the forces within matter. The black hole is gravity unchained, the end of resistance, the pure shape of space-time, when nothing stands against it. Both are stable, both eternal in their own way, but one still remembers its origin in matter, while the other is pure form. To see them as opposites is tempting, but incomplete. Together, they form a continuum, a single progression of collapse. The neutron star's crust, its pulsations, its radiation, all foreshadow the black hole's silent depth. The black hole, in turn, inherits the neutron star's mass and density, pushing them beyond all limits. They are two notes of the same cosmic chord, separated by a single step across an invisible line. This continuum carries meaning beyond physics. It reminds us that every structure, no matter how enduring, has a point where it yields. The neutron star teaches that resistance can reach astonishing strength, but never infinity. The black hole teaches that even surrender has form, that disappearance can still shape reality. Between them lies the entire philosophy of existence, the balance between holding on and letting go. In the light of science, they are equations. In the light of wonder, they are symbols. The neutron star is gravity's masterpiece order, sustained at the edge of collapse. The black hole is gravity unchained, the surrender of matter to the purity of curvature. One bends the universe, the other consumes it, and together they define its limits. The universe itself is built upon this balance. Stars are born, live, and die within its boundaries. Galaxies form, evolve, and fade according to its rules. Even time and space, vast and indifferent, trace their meaning back to the same law that governs these objects. Mass curves, geometry. Geometry dictates motion, and motion becomes destiny. If there is poetry in the cosmos, it is written in these curves. The arcs of light bent around black holes, the pulses of neutron stars ticking through eternity. Gravity, in all its forms, is both sculptor and stage. It binds everything that exists and defines everything that can be known. And so the story of gravity, from the birth of stars to the fall into darkness, is not a tale of destruction, but of transformation. Each collapse gives rise to new structure. Each disappearance births new light. The black hole and the neutron star are not ends, but beginnings of a deeper understanding, the realization that the universe is not static, but forever in motion, folding and unfolding upon itself like a living equation. In the end, there is no true boundary between light and dark, between resistance and surrender. There is only gravity, eternal, patient, and exact, shaping the universe from within and without. The neutron star whispers its defiance through pulses of radiation. The black hole answers with silence. Between them, the universe listens, and from their dialogue, everything that exists finds its place.